The moon just broke its own origin story. For decades, I learned that a global lunar magma ocean slowly cooled over millions of years, floating light anorthosite to the top to build the moon's crust. But brand new research from Lawrence Livermore National Laboratory and collaborators says, nope. The moon may have solidified shockingly fast, on the scale of centuries to a few thousand years. Let me unpack the bombshell. The classic picture goes like this. A giant impact forms the moon. It's a glowing ball of melt. As it cools, dense crystals sink, light crystals float, and over a long, leisurely timeline, you get that pale anorthosite crust we see today. Slow cooling fits with a lot of early models. It's tidy. But nature doesn't owe us tidy. The new work pulled together high-precision chemical clues from lunar rocks, with high-precision isotopic clues, and fresh thermal modeling, and found something that doesn't square with the slow story. If the magma ocean took millions of years to crystallize, the isotopic clocks and elemental patterns should look one way. They don't. Diffusion profiles, incompatible element distributions, and model constraints line up much better if the ocean locked up way faster. Think centuries to millennia, not geologic eons. Why does speed matter? First, structure. A rapid freeze changes how crystals separate. Different layering pockets of trapped melt, and a crust that forms in pulses rather than a slow drizzle. Second, heat. Quick solidification means the moon sealed in heat differently. That affects early volcanism, how quickly the interior stiffened, and when the crust became strong enough to crack, slump, and build the basins we map today. Third, the core and magnetism. The moon once had a surprisingly strong magnetic field. A faster cooling mantle changes heat flow into the core, shifting the timing and intensity of the lunar dynamo that magnetized ancient rocks. Fourth, Earth-Moon evolution. Rapid crust formation means the moon's surface became a rigid lid early on. That tweaks tidal heating, orbital evolution, and how the moon's distance from Earth changed in the first tens of millions of years. It even nudges how we read crater ages and volcanic episodes we see from orbit. So what flipped the script? High-resolution measurements of lunar samples, Apollo anorthosites and related rocks, carry isotopic fingerprints that act like timekeepers. When you compare those clocks against models that include realistic crystal mush behavior, convective heat loss, and how elements partition between crystals and melt, the slow ocean struggles, the fast ocean fits. Does this mean the LMO is wrong? Not exactly. The magma ocean still happened. What's being rewritten is the tempo. Picture less simmer, more flash set, driven by efficient heat loss, rapid crystal formation, and limited time for the melt to stay mobile. Here's the exciting part. A faster moon reframes mysteries. Why some lunar crust looks surprisingly uniform, while other regions scream diversity. Why certain volcanic glasses tap deep, primitive sources. Why some isotope systems seem out of sync with a lazy cooling timeline. The fast freeze moon ties those threads together. This isn't the final word. New sample analyses and models will stress test the idea. But if it holds, we're not just tweaking a chapter. We're revising the opening pages of Earth-Moon history. So next time you look up at that bright, ancient face, remember, it may have set faster than a soufflé. And that changes everything about the story we tell of home.